Hi, this is Roger from Kanker Labs today with a little journey into the past. Now, here in Germany there is a famous publishing house called the Franksche Verlagsgesellschaft, and they are not so famous for their books or magazines, but more for their KOSMOS experimental boxes dealing with every kind of science and built for teens and twins, or children, teens and twins, and they exist for more than 100 years, and perhaps their most famous customer was Wernher von Braun, who not only built the V2 rocket but also the Saturn V to bring us to the moon. So, and before I got interested in electronics, also with some of their experimental boxes, which I will perhaps, if I find the time, demonstrate to you in a future episode. Anyway, before that, I tried some of their other experimental boxes, and this one here is called in Germany the Elektromann, which simply translates to Electroman in English. And it deals with all kinds of electrical and magnetic phenomena, electromagnetism. And you can see some of the experiments built up here, which we will try out in a minute. You see, you get two of these mounting plates where all the experiments are built up. And everything is explained from the basics, how an electric circuit works with light bulbs and batteries, that the circuit has to be closed so that current can flow, then electrostatic phenomena. You can build a Morse telegraph and anything else. And here, for example, this is a carbon microphone. This is the only thing I did not get 100% to work. Or the counterpiece, the model of a loudspeaker or of a headphone, which I will demonstrate in a minute. Or an electrical DC motor with reversible directions. If you wonder where the batteries are, they are mounted here down below. Originally, these are 4.5 volt batteries, but today it's easier to have, and you can see here the needle is just swinging around because of the magnet here has come too near. Anyway, today you get these adapters for AA cells to get your form factor of a 4.5 volt battery. And quite interesting, the model, or not only the model, a working example of a moving magnet ammeter. And we will check the accuracy of this later, which I never could as a boy because I didn't have a real multimeter at that time. So I bought second hand on eBay 3 incomplete old experimental boxes, and I made 2 complete sets out of them. One got to my nephew, and the other one I kept just to build up permanently these 4 experiments. So the top experiment out of the more than 100, which was quite at the end of the explanation book, was this DC motor. You had to wind the windings here on the motor core for yourself, and you can see here you have your collector which puts the power always to the next coil, etc. Here you have a permanent magnet and the yoke where the magnetic field lines are directed to. Oops, and it already started here. And of course there is no way provided to suppress any EMI. That was not necessary at that time. So perhaps if I activate it, you can see the little sparks here emanating. Let's see if you can see it. I don't know how good it comes out on camera. And it makes a lot of noise. So when I was a boy and I built this up, this thing never turned very fast, and only with the patience and experience I got later when I became older does this thing now turn so fast in one or the other direction. And so I'm quite proud that I could get this and rebuild this and make it working much better than in my use. And so the next thing is this model of a loudspeaker or headphone. As you can see also, we have here an electromagnet where we will just connect it to a frequency generator. Then you again have here a little soft iron core and this yoke here and this little lid here made out of sheet metal or tin plated sheet metal. This just fits over here, and of course by the changing magnetic field, which is concentrated here with the soft iron core, this acts like a membrane which is either attracted or rejected by the changing magnetic field. So let's try this out. I'll have to get it attached again. I'll just connect it with a frequency generator. We'll input a sweep wave. Perhaps you can already hear it from, I think, 400 Hertz to 5 kilohertz. And now I will take my microphone out so that you can better hear it. So I hope you could hear the sweeping frequency on this little. So it's not a model, it really works. And this is one half of a telephone. The other half is, of course, you need still a microphone, and this is also the working model of a carbon microphone. Here this acts like a sound funnel, or however you want to call it. And here in this compartment there is the carbon, the graphite, and so this does not work very well, and it's next to impossible to demonstrate this on camera. But as the last, where has the needle gone? There it is. As the last, look what they thought out here. An ammeter with a compass needle as a moving magnet, and then a winding tapped here at 2 turns, and then 40.5 for 2 different scales. So you can see the right scale is for high currents up to 1.5 amps, and the other one is for the lower currents starting at around 1 milliamp. And I wonder if this thing really can display 1 milliamp. And of course the scale is non-linear because simply the relation between the angle of the compass needle and the strength of the magnetic field is non-linear. So it's at best a cosine or perhaps a tangent function, whatever. So I will reconnect this just to demonstrate it, and let me have a little break just to build the experiment up. So here we are back, and such a compass needle has an astonishing sensitivity. It took me some time to find out why the needle was moving already when I only came near to the contacts here without any current flowing. And the reason is that these grabbers here, they are magnetic themselves, which I never would have thought would play any role in any experiment, but you can see it does play a role. And of course it doesn't always return due to friction to its 0 point. And as you can see, I had to turn it, of course, so that magnetic north is exactly in this direction. And it even makes a difference if I take the shiny side of the compass needle or the black side as a pointer. And we will try the more sensitive range here. And first of all, let me get the leads. You can see here are the connections for the current to measure. And let me see what we got here. If it already reacts. This is the wrong direction of current. So it's a bit awkward for me again here in front of the camera. And we have, you can see it at the moment, 8 milliamps. And it even reacts a bit too much. So what's going on? Okay, we have 8.6 milliamps displayed where my arm is at the moment on the display of the multimeter. And our moving magnet ammeter displays something around, I think, 20 milliamps. So let's put in a higher current of 50 milliamps. And we now have 47 on the display. And it already goes to full swing to 100. So it's 50% off. But concerning the crudity of our experiment, because the compass needle does not have a reproducible magnetism, this is still quite good. So let's see if we can measure a very low current of, let's say, 5 milliamps, something in that range. We now 3.9, and the needle moves a little bit when I make contact. You can see it. So anyway, the principle of the measurement is verified, and you can even measure down to, now we have 4 milliamps, down to the lower milliamps region. So let's go to the lowest. I can set this 1 milliamps set, giving us half a milliamp, true. And can we see a movement of the needle? Yes, it moves a little bit. If you watch closely, so we can even measure a little bit below 1 milliamp with this crude experiment. So I find that quite astonishing. And it's not so much about the precision or non-precision of this experiment, but that it works at all and gives you an idea how an ammeter works, that it depends on the magnetic fields and that you can create this magnetic field here with a coil, and depending on the turns of your coil you get different scales, one for the amps region, one for the milliamps region. So I find this quite interesting even today, 40 years later. And sorry, KOSMOS, in the US they are, as far as I know, known as THAMS KOSMOS. They are still making experimental boxes, but they are not as good as they were in the 1960s and 1970s. But that is, of course, a subjective view from my experience from my childhood. So I think that was it for today. If you liked it, please give it a big thumbs up. Then I perhaps will pull out some more of my old experimental boxes from other fields of science. And thanks for watching. Until next time, bye from Roger, bye from Kanka Labs.